So, chapter 4 of section 1. I don't know how easily you can even see this. There's these little guys under there. It's the microscope field. And it says, do your stuff, you're on microscope. We're going to talk about microscopes, just a little bit about cells, because cells will come up now and again when we get into the bigger living things. Microscopes were developed through the 1600s and 1800s. Now, people had been making magnifying lenses for as long as they had been making glass. I mean, if you make glass and you get glass that comes out in the right shape, you can see that it magnifies stuff. But putting two magnifiers together took people a while to figure out. And then it turns out, okay, how do you make a magnifying lens? Well, it's thick in the middle and thin on the sides. And if you've ever dealt with a prism, which is triangular, the light goes in and it separates. It comes out, the different colors come out in different spots because the glass is different thicknesses. And that was a problem with with potentially microscope lenses, that you could see things, but they had these auras, these colored auras around them from the different thicknesses of glass. And so it took some fiddling. A fellow named Leeuwenhoek is considered the granddaddy of microscopes. He didn't actually make microscopes, he made lenses. And he made lenses that worked very, very well and kind of solved a lot of the prisming problems. Once people had microscope systems, though, you need lots of light. Most of the microscope stuff was done outdoors, where you could use sunlight with reflective mirrors and stuff, because there were no, the light you get from a flame just wasn't enough. Once they had microscopes, a lot of cool stuff happened. Malpighi, whose name will come up later when we're talking about insects, took living goldfish and laid them down under microscopes, looking at their tails. Goldfish tails fairly transparent. Under a microscope, you can see the blood coming out and going back. And if you were to slice it, blood would come out of the blood vessels. Now, at that point, people knew blood would leak out of you. They knew that your heart somehow moved the blood, and they knew that there were tubes, but they only knew about the big tubes. If you don't know about the little tubes, then you don't know the blood circulates, that it goes out, eventually goes through a whole bunch of little tubes and comes back. The arteries take it out, the veins bring it back. Well, from dissecting animals and people, they knew about the arteries and the veins. They weren't really sure what they were doing there. They thought the blood was just kind of created in the heart and spewed out to everywhere. But now Malpighi, seeing these tiny blood vessels taking blood out and back, was the first indication that we have a circulation system, that it's all loops. Robert Hooke in England took cork and sliced it really, really thin, cork from trees, and under his microscope, he could see that it had a lot of little chambers in it that kind of looked like rooms in a prison. He called them cells. Now they were, if you have a piece of cork, it's got the cell walls of the cells. It doesn't have living cells in it anymore, but we call the living parts the cells now. So lots and lots of stuff. People started to look at pond water and saw these little things zipping around. And for a while, spontaneous generation kind of made a comeback. Because it also turns out if you take a drop of India ink and you put it in water and look at it under a microscope, the small particles, just from the molecular movement inside, they dance around. And people knew the India ink wasn't alive, and yet the spots under the microscope looked alive. So the idea that non-living things could become living things on a microscope level it took a while for that to go away. And we'll cover that a little bit later in the chapter when we come back to cell theory. Now for modern microscopes, there's one feature that is probably the most important feature on microscopes. It's also a very important feature on things like telephones and video screens and TVs. It's called resolution. Basically, resolution amounts to how clear does it make it? How good can you focus what you're looking at? On screens, like you're looking at this, a resolution is measured by the little dots that make the picture show up. The more dots per a particular square space, then the more fine you can make a focus. Classically, under microscopes and with other kinds of lens things, resolution was determined by saying, okay, you have two items. If you've got really good resolution, you can see there's a space between them. As the space gets smaller and smaller and smaller, now my fingers are not touching, but on the screen I'm looking at, it looks like they're touching. Now part of that is the angle. But there's a point at which that space seems to disappear, that the two items look like they run in together. And classically, resolution is measured by what's the smallest space that you can see is still a space. At what point do you lose that? Because we think about microscopes and we go, oh, magnification, magnification, magnification. But you know as well as I do that if you take a picture that's out of focus and you make it bigger, you get a big picture that's out of focus. Focus is more important than magnification. Is that how big you can make it is only useful if you can clearly see at the higher magnification. Now there's two major, what they call imaging systems that we use. There's a few weird ones, but there's two major imaging systems that use different types of beams. In the lab, we turn on the light and we look at this through the scopes. Those are light microscopes. When you get to about 1200 magnification, that tiniest space that you're trying to see, the light beams have a wave. They have a height to their wave, and that space starts to get about the same size as the light waves. So they're no longer able to squeeze through the space. The two items look like they're together. So a light microscope, or just a regular, good, really good light microscope, hits its resolution limit somewhere around 1200 magnification. The ones that we have in the lab go to 1000, and we don't even use the 1000. We don't look at things small enough to need to use that. But people want to see smaller things than that. Electron microscopes have an electron beam. They shoot a beam of electrons. Now electrons are teeny, teeny, tiny little particles, smaller than atoms. And now you can't use a glass lens in an electron microscope, but electrons are charged particles, so you can focus them and then expand the picture like you would with a lens, except you use magnets. So electron microscopes focus with magnets, but their resolution, if you want to spend a few $1 million on one, you can actually see atoms with them. Is that, now I did my research on electron microscopes, and it was a fairly expensive piece of equipment, but way more expensive than a light microscope, but nothing I could see atoms with. I'm going to talk a couple of things about using microscopes, and then I'm going to come back and talk about the differences here. So you're not going to need to put a lot of stuff here. You may want to leave yourself some space under the electron microscope bit. I'm just not putting it that close because I'm not gonna fit all this stuff in. Oops. Sorry, I should have put this up above. You definitely need to leave yourself room for this. Then you can put it in there out of order. There's two basic imaging beams. There's two basic ways that the beams interact with what you're looking at. A transmission scope, the beam comes through what you're looking at. It's transmitted through the item you're looking at. A scanning scope, the beam bounces off the item that you're looking at. For the classification lab, there are two different types of microscopes I have out in the lab. If you're doing this remotely, you got two different types of pictures that you could see. Where in one there was a light field and you could see through things. And then for dissecting scopes, which are a type of scanning scope, you would see the surface of the object. The beam would bounce off the surface. Because a transmission beam can be held together fairly tightly, it tends to have better resolution. You can see bigger things better, or more magnification better. Scanning, since the beam bounces in all directions and then you've only got one thing to capture it with, scanning scopes tend to have lower resolution, but you see things in three-dimensionality, which is kind of cool. For a transmission scope, you gotta have problems with the beam's gotta come through, but you don't want it to come through so well that you can't see what you're looking at. So items have to be semi-transparent, transparent enough that they're not just a silhouette against the beam, but not so transparent that you can't see them with the beam behind them. That's what sectioning is for. Sectioning takes an item that you're gonna put under the microscope and slices a really thin slice out of it. And then you put it on a slide and the beam comes through. Or in an electron microscope, you put it on a grid and the beam comes through. An electron microscope, the sections have to be really, really thin. Typically what you do to make sections is you take a material, you preserve it, put it in preservative, then you put it into some sort of material that will hold together when you slice it really thin. For light microscopes, that's typically a wax. If you have a biopsy, it goes to a lab, they embed it in a block of wax, and then they slice really thin sections out of it, sectioning. My daughter does that. And of course, in my research, I did that as well. But when you've got thin slices of tissue, again, transparency becomes an issue, and very typically you take that thin slice and you treat it with different dyes. Different types of chemicals will pick up different dyes. So one sort of cell will stain red, and one sort of cell will stain purple, and one sort of cell will stain green. And so you can look at the sections and then stain them. Like if you have a biopsy, they have a special stain that will only attach to cells with cancerous chemicals in them and stain them slightly brown. And so the biopsies, they put it in wax, they slice it really thin, they put it on a slide, they make the wax go away, they stain it, and then it goes to a pathologist who looks for the brown stain as an indicator of there being cancer cells. If you've got a really, really small, like a little bug or something, which we look at for the introduction to microscope lab, then you want to do what's called clearing. You want to put them in a chemical that leaches a lot of their pigment away so that they're not a big silhouette, so the light will come through them. And sometimes you need to stain that also in order to make stuff show up. So these are all important items having to do with both of these types of microscopes. Now I'm going to start talking about how electron microscopes are different than light microscopes, above and beyond having better resolution. They are way more expensive. We have one electron microscope in the building. It's down in the basement. I've never used it. Actually, they asked us what kind of scope we wanted. biology people said, we'd like one we could look at biology stuff in, and they got one that you look at electronics with. You know, you can look at chips, so we don't use it. But that's it. We could only afford the one, and I think we got a grant in order to get the one. In my university, there were 2 electron microscopes. There was a transmission scope and a scanning scope. And I'll show you some pictures that I took from the scanning scope in a second. So they're expensive. They're much more complicated. Is that when you sit at an electron microscope, there's a whole array of different controls that I did a couple of years of research with one. I probably don't only know about what about half of the controls do, because some of the controls you use on things like chips and other kinds of things. So, but they're very, very complicated. Any day I was going to use the electron microscope, you get there early, you go in, you flip the switch, and you hear dum, 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 dum. All of the air needs to be pulled out of the middle of the microscope. An electron beam is full of tiny little particles. You can't have air in there. Air will bounce the beam all over the place. And so you gotta have a vacuum. That's different. Electron microscopes need a vacuum inside, which means you can't put living things in there. You can't put drops of water in there. Anything you put in there has got to be really, really, really dry. So preparation becomes an issue. Is that I was preparing my specimens, and at the last step they go, okay, take your specimens and put them in that little cylindrical thing, put them in the bomb over there. And you go, the bomb? You go, oh yeah. Every once in a while, because it's a real high pressure environment, every once in a while one of them will fail and explode. It's killed a few people, not in our lab, but we've heard about people in labs getting killed by it. So people call it a bomb. Be careful with it. So electron microscopes, there's some dangers involved. You do have to section and stain. You don't use wax to hold the tissues together because you have to slice them so thin you use actually broken glass to do the slicing. And the stains have to be stains that show up and interfere with an electron beam. So they're heavy metal stains. Electrons, what you see in the picture is all black and white. It's either the beam hits the screen or doesn't hit the screen. And if you see a colored image, somebody came in and photoshopped colors onto it. But the staining is very toxic. You have to be really careful doing the staining. So electron microscopes, they're more expensive, they're more complicated, the prep is more complex. They have to have a vacuum inside. The stains are more dangerous. Is that in order to use it for a scanning scope, you need to coat the surfaces of what you're looking at with gold or platinum so that the electron beam will bounce off and not get absorbed. So it's only 1 atom thick, but the thing that does it is pretty expensive. So again, expense. So that's how the 2 different types of devices, the light microscopes and electron microscopes, are different. Okay, let's see what I got. This is a negative that I took off of the electron microscope. Is that it used a type of film that I had never even seen actively used. I knew that it existed. It was cameras from like 50 years ago. Really expensive to get by the time I was using it. Probably, now they're all digital. But that is the head of a fire ant. A fire ant is an ant that you find down south, but around here, the little piles of sand with little red ants in them. Fire ants are about that size. And that's the head of one, where that's the head. Where's my little pointer? That's the head. These are the mandibles. These are the antennae. You can't really see the eyes on this one. This background light isn't quite strong enough. I don't know if I flipped it over, whether it be. Yeah, maybe. The eyes are there. But just to give you an idea how the world works. This is a piece of the antenna. Lots of sensory bristles. You can see they're slightly flexible bases so the bristles can move and they can feel things with them. Here's a bristle with a little friend on it. So this is the antenna, that's the tuft at the end. And this is a mite. A mite is an animal related to spiders. And as you can tell from that, this one's pretty doggone small. We have cells this size, but this is an entire animal. It's, these are feelers in the front. They don't have antennae, but these are the legs. This is the carapace. There's a couple of feelers in the back. That's the exit of its digestive system. The mouth is up there. So it's got a whole digestive system and circulation system and nervous system. All the animal systems we're going to talk about, you can find in these animals, and they're teeny, teeny, tiny, and they have teeny, teeny, tiny cells. I mentioned with peer review that I put down how to, in my paper, how to prepare the animals, and the guy went, everybody knows this, and I went, well, it's not written down anywhere, and they let it go. Here's the problem I ran into. Drying the animals out made them distort. And it took me a while to figure out how to get them to look normal with the preparation method that I had to develop, that apparently other people in other labs already knew how to do. But these are scanning electron micrographs of the outside of a roundworm that is a tiny parasite inside the digestive system of minnows. So the worms, I mean, minnows are pretty small, digestive system's really small, these guys are really small. This is just the surface of one of the worms. This is how it's supposed to look, this is how it wound up looking. This is how it's supposed to look, this is how it wound up looking. Okay, good place to stop. We'll pick up cells next one.